Good day. I'm Norman Wildberger. This is one of a series of foundational videos on mathematics. In particular, we are looking towards establishing proper foundations for geometry. And so in the last few videos we've been looking at Euclid's Elements, which is the most important book in the subject and has a lot of interesting things to say about foundational issues for geometry. Now today we're going to have a very brief look at books 6 to 13. Last video we talked about book 5, which established Eudoxus' theory of proportions. Book 6 uses that theory to talk about similar figures, in particular similar triangles. So these two triangles are similar because they have equal angles. And I remind you that by equal angles, Euclid means that if you take that configuration, which is what he called an angle, and you move it over here, it fits right on top of that. So if these triangles have equal angles and so are similar, then there are certain relations between the proportions formed by these magnitudes and the proportions formed by these magnitudes. Now remember, it's very important to remember that Euclid did not use numbers to describe the lengths of sides. He thought of a magnitude, like a length, as an independent quantity, independent of any number system. So the consequence of the similarity of these two triangles is in these proportions between magnitudes. That A to B, that proportion, is equal to A prime to B prime. And similarly, B to C is B prime to C prime, and A to C is A prime to C prime. All three can be put together in the one single proportion, A to B to C equals A prime to B prime to C prime. The books 7, 8, and 9 concerned with number theory, and they're not directly connected with our approach to geometry right now. Book 10 is dealing with incommensurable numbers. For example, Euclid shows how to geometrically understand what we would call as a number root of root 2 plus root 3. So this nested kind of radicals. It's books 11, 12, and 13 that are quite interesting because that's when Euclid branches out into solid geometry or into three-dimensional geometry. And there are a lot of interesting and difficult results in these books, culminating in sort of the grand finale of the classification of the Platonic solids. So let's just have a quick look at some of the issues that are raised in these books. Euclid begins by some definitions. For example, a solid is that which has length, breadth, and depth. An extremity of a solid is what he calls a surface. He defines planes. He defines what it means for a straight line to be at right angles to a plane. It's at right angles when it makes right angles with any line in the plane which meets it. There are many other definitions of spheres, solids like tetrahedrons and convex bodies and prisms. But it's probably fair to say that these definitions aren't completely satisfactory. You really have to have a sense of what these things are beforehand in order to understand what he's talking about. In fact, in general, these latter books represent Euclid biting off a little bit more than he could chew. It's just a fact that three-dimensional geometry is a lot harder than two-dimensional geometry. And that's manifested in these books in that a lot of the theorems are not quite logically correct. There are gaps, there are weak points, there are times when he only proves things in special cases. But nevertheless, there are a lot of interesting results and important results. For example, proposition 2 of book 12 states that circles are to each other as the squares on the diameters. He's saying that if you have two circles, then the proportion between their areas is equal to the proportion between the squares on the diameters. In our language, that's saying that the area of a circle is proportional to the square of the radius, or the square of the diameter. That's an important result that Euclid knew you can't just take for granted. It has to be demonstrated, something that's almost universally never done in modern courses in mathematics. How did he do it? he went back to his friend Eudoxus. Eudoxus had developed something called the theory of exhaustion, which is an approach to areas of, say, curved regions by inscribing polygons, and then in a sequence of steps approximating the area of the curved surface better and better by these inscribed polygons. And in this case, what that amounts to is if you have a circle and you put a square inside it, that's a first approximation to the area. Then the next approximation is obtained by taking the midpoint of this arc and joining it to form a little isosceles triangle. You do that at each one of these sides to form an octagon. And the crucial point is that this triangle that you've added is more than half of the area of that arc there. The reason we know that is because if you put that arc inside a rectangle, that one there, then the area of this triangle here is exactly half of the area of the rectangle. And so it has to be more than half of the area of that arc. And so that's the basis of this theory of exhaustion, that if you always go more, if you take away more than half of what's remaining, then eventually you will get something approaching zero. So there are many other results in these books, but the final grand culmination is the construction of the 5 Platonic solids: the tetrahedron, the cube, the octahedron, the icosahedron, and the dodecahedron. Altogether, Euclid's achievement is a remarkable one, and it's no surprise that it established the foundations of mathematics for 2,000 years afterwards. However, cracks did appear, and we've already mentioned a few of them. Next time, we're going to have a better look at some of the difficulties that arise with Euclid's geometry, towards our goal of replacing it with a simpler and better approach. I hope you'll join me. I'm Wildberger. Thanks for listening.